In this video, we will talk about the Solow-Swan model, which is probably the most influential growth model that has been ever developed. It hasn't been the first one, but it still is influencing the way, especially the economic mainstream, is doing growth theory as of today. So it's very important. But before we go to the Solow-Swan model, let's look at the historical vantage point. Probably the first mathematical growth model has been developed by other people. Roy Harrod, Domar. There have been mathematical models before as well, but this was the first one that was really influential and focusing on the topic of economic growth. It has been developed in a time of still influenced by the Great Depression. So these people were witnessing a lot of economic hardships in the society. They were very much influenced by the Keynesian revolution, or the upsway of Keynesianism. So the idea that the state needs to be an important actor in economic policy, has to be active, has to do things, need to spend. It has also been the period of the Cold War, and it has been a period where especially the Soviet Union has been experiencing a lot of so small victories. So Sputnik, so the satellite was successful in that time. So the idea of having an economic system that is built on economic planning has been considered to be something really serious. And many economists actually were arguing towards more economic planning in this time. And it was this context where the Harrod-Domar growth model was developed. It's a mathematical model, so it's based on a certain number of key relationships. Most important thing here, probably this equation that basically explains the Y, so the total production of the economy, and it relates Y to the capital stock K, and a constant, V, the capital output ratio. Very important, this was a constant, it was a parameter given to the model. It's nothing that changes endogenously. It then has an equation for total savings, which is basically the savings rate times total income. The investment rate is set equally to the changes in capital. So there was a clear relationship between capital accumulation and investment as of today, and also between savings and investment. As of today, there's a huge debate about what comes first. For a long time period, people were thinking, okay, there need to be savings first before there's investment. In our current monetary system, that's definitely not the case, but the two need to be the same by definition. And from these relationships, they derived three different growth rates. The first growth rate is the percentual change of big Y. So the percentual change of total production. So the actual growth rate you're seeing in the data, so to speak. The second GW is the so-called warranted growth rate. This is the growth rate at which the entrepreneurs are fulfilling their own expectations about what's happening, and they are operating at the exact capital output ratio they want. So on the economy level, you see the V on the left side, the economy-wide capital output ratio, and the warranted growth rate is the growth rate of the economy, where for every single entrepreneur, he or she is happy with the capital output ratio he or she is working with. In this case, also, there's a full utilization of capital, and the desired investment of the entrepreneurs equals their actual investment. This is, of course, an implication of the desired capital output ratio they have. And the third growth rate they look at is the natural growth rate. The natural growth rate is basically given by the growth of the labor force and technical change. Both basically external parameters to the model. They are exogenous, so they are not determined by the model itself. And it's basically a measure for the maximum growth that is feasible given the current state of the labor force and population growth and the technologies available in the economy. And the issue with this model is, mathematically, it is only stable if these three growth rates are the same. Now, the actual growth rate is given by the data. The other two growth rates are given by the parameters you put into the model. And, well, it's your decision to some extent what kind of parameter values you set. And the issue with the model is, if they are accidentally the same, the model is stable. But if there are only a tiny deviation among them, there's cumulative instability. So it's not the case that the economy is correcting towards a situation where they all three become equal, but rather there's cumulative instability. Mathematically speaking, the situation where the three rates are different is a repeller. So if you are not in this point, the economy will developing away from that point. So there's cumulative instability. For Harrod and Domar, the conclusion was that there are no self-correcting forces in the economy. There is an inherent instability, so there needs to be constant intervention to push the economy towards the situation where the three growth rates are the same, because otherwise it will never reach it endogenously. And you see, this obviously relates to the economic or to the socioeconomic context these authors were experiencing. And it is therefore basically a model that in some sense formalizes this idea of the inherent instability of the capitalist system and the need for Keynesian interventions. And then there was the Solow-Swan model, developed by Robert Solow and Trevor Swan. They didn't collaborate, but they actually published the model more or less on the same time. Robert Solow has become super famous. He also won the Nobel Prize for Economics. Trevor Swan remained rather unseen figure in economics, unfortunately. It's only people who really look into the history of economic thought who actually appreciate his role. He was somebody who wasn't publishing a lot. Actually, a lot of his works were published only after his death, and then people figured out that, hey, this is actually really great stuff. He was also facing a lot of health problems. And then again, Robert Solow was also part of the very influential MIT faculty of economics. So he obviously also gained a lot of more visibility for institutional reasons. But we still call it the Solow-Swan model because it was basically developed by both of them more or less at the same time. And this model was super important in the sense that it solved the instability problem of Harrod and Domar. I say problem because for some people it might not be a problem at all. It basically shows the internal instability of capitalism. But like from a scientific viewpoint, it was obviously something many people were not really happy with. So Solow and Swan came up with a number of key innovations. Above all, in the Harrod and Domar model, you had inputs from labor and capital, and when you were looking at production, there was no way to substitute labor for capital. And Solow and Swan came up with a production function that actually allowed for factor substitution, and where firms could, for example, invest more into capital, thereby substituting workers. Or say, okay, capital is too difficult to get at, we hire more workers and work with less capital. So this factor substitution was introduced by them. Also the idea of diminishing returns. We say, okay, to some state, the additional marginal gains from capital become less and less. Because you have almost no capital, a little bit more makes a huge impact. You already have a lot, more is still better, but the returns are diminishing as compared to the situation where you had little capital. The implication of that was that the instability of the Harrod and Domar model goes away. And there's stable growth path possible without any state intervention, but where the model economy is basically self-correcting. Also, from a scientific point of view, very important was that they opened the door for micro-foundations. So the parameters they were using were not fully exogenous in the sense that they had to be assumed from the outside, but that they could be derived from microeconomic theory about how firms actually make decisions. Now, there is a lot of debate about whether this microeconomic theory is good or bad, whether micro foundations or this focus exclusively of micro foundations is a good idea. But it has definitely been an innovation that has made their model super appealing to many other economists at that time. If you look at the equations, again, this is the Harrod-Domar equation that I showed you on the last slide. This is the equation that Solow and Swan came up. So again, they were focusing on big Y, total level of production. For them, it was a function of capital and labor. And they used these superscripts, alpha and 1 minus alpha, to indicate the relative share or the relative contribution of these production factors to total production. And you see from this function that it is fully possible to substitute capital for labor, or vice versa, because you just can. It works through the adjustment of the alpha parameter. There's also this is a mathematical implication of how you define the function, that you see diminishing returns for both factors. And here are a little bit more details. So in absolute terms, this is what I just showed you. This is probably the most famous version of the model. But actually then, if you look at papers, if you look at the earlier papers of Robert Solow, he was not looking at absolute output and the growth of absolute output. He was looking at the whole thing in per capita terms. Why? Because, well, it's often from an economic viewpoint, it's more interesting to look at per capita terms. Because like the absolute size of an economy, of its total production, is to some large extent like determined by the size of the country. Of course, China will most likely have a higher total production than, for example, Switzerland, because there are many more people in China. But what is important for the welfare people are enjoying, it's often the per capita version, and you come from the absolute Solow version to the per capita version by dividing by L, by dividing to the size of the labor force. Of course, this is not the same as dividing by population, but it makes many things a lot easier. You also see, for example, that the big L goes away in the per capita formulation, because L divided by L equals 1. And if you see the small letters in this formulation, that always indicates that we are looking at per capita terms, per capita in the sense of per worker. And in the following, I will focus mainly on this per capita version, because it's the version you see mainly in papers. So here you see the small y is actually nothing but the output per worker, and the small k is just the capital used per worker. So when using the small letters, this is what's behind it. And by dividing everything by L, we basically get rid of this one variable in the equation that also makes it easier to work with the model later on. The fact that alpha is basically between 0 and 1 implies that we have diminishing returns to capital, also to labor, but here we are only looking at capital. If alpha was larger, we would have increasing returns to capital, but as I said, Solow and Swan focus on this case because they made this argument that diminishing returns to capital are more relevant. It's what we can derive from microeconomic theory. And to be very honest, it's also at the source of the problem of the model solving this instability problem of Harrod and Domar. If we look at the change in the capital per worker stock, we're looking at the change of small k, so delta k. And this is basically the same as investment minus depreciation. Now we have this depreciation parameter delta. And if we want to look at the change of the capital stock per worker, we look at, okay, how much capital is being built up via investment, minus how much capital actually goes away because of depreciation. Therefore, this idea, investment minus depreciation, this is called the equation of capital accumulation. Yeah. So here it's in a little bit more detail. The change in the capital stock per worker is savings times total production. So that's investment, because saving is also considered to be equal to investment. Huge debate later, but here that's how it is. Minus delta, depreciation parameter, times capital stock. Yeah? So SY, capital accumulation, delta K, capital depreciation. You basically can, if you insert the definitions from above, you get this second version of the equation of capital accumulation, SK alpha minus delta K. Yeah? Just insert the definitions from above and you get to exactly this formulation. Okay, so that's what I'm basically saying. Investment adds to capital stocks, depreciation reduces it. And the steady state, so the equilibrium of the whole thing is where investment equals depreciation, because this is when the capital stock actually remains the same. How do you find the steady state? You find the steady state by setting delta K, so the change in the capital stock per worker, directly to 0. So you're saying, okay, this is basically the situation I want to look at. If you have that, you can basically rearrange the equation you just saw, and you can basically say, okay, SK alpha equals delta K. Implication from above, because the change in capital is SK alpha minus delta K. So if we set the change to 0, we can basically say, okay, they both need to be the same. Then you can solve this for K. K star is usually considered the equilibrium value of the whole situation, and you get to this equation here by just rearranging the equation from above. And at K star, you can also compute a value for Y star, and both of them are, Y star is constant at the value of K star. So there is no per capita growth. That does not mean there is no growth of the economy. So absolute growth can be there. So big Y, the thing we're not looking at here, might grow, but small y, GDP per capita, does not grow. Absolute growth is determined fully by population growth. So if the worker population increases, so does total production. This has been the simple version. The actual model also includes technology, which is usually referred to by big A. But technology is also a little bit, as we will see later on, it plays a weird role in the whole Solow model because you basically consider it this way. So it's technology is basically augmenting the output you get from the inputs. This is also why we say technology is neutral in the sense it improves basically all factors of production. It's fully exogenous. The Solow model doesn't contain any theory of how technology changes. That basically means technology has similar effect than population growth. Yeah? It just boosts the whole production. And it determines total growth just as population growth. But people say it falls from heaven. The Solow model doesn't contain any theory of technological change. It's just there. But this is super important for the implications. And one reason for why the Solow model has become so influential is this. It's the diagram that actually shows how the model reaches its equilibrium. It's a very nice way of visualizing the whole mathematical argument. And it is basically one reason, I guess, why the model, so many people like teaching this model, because you have this nice visual arguments that are mainly due to Solow's work. That's probably also one of the many reasons why he has become more famous for this model. Okay, so first thing you note when you look at this figure is that you have all the variables with the little hats. This is because we're here talking about effective workers or effective production. So we adjust the whole thing for technological change. So they basically represent the output of a worker given the technological change. This is important for the visualization to work, and maybe it becomes more clear if you look at theories of endogenous growth, where technology plays a bigger role. But for now, it basically doesn't augment the overall argument, but it's important that you see, okay, these hats basically mean we adjust the whole thing for technology. Now, the three lines you see there is, first of all, the blue line. That's the line for the total output. That's the total production per capita per effective worker, controlled for technology. So you see in the definition of the blue line, that's basically our production function. Then you have the red line, that is basically the investment function. It's the function that defines investment as being basically total production times the saving rate. And as I said in the beginning, investment is the thing that actually increases the capital stock per worker. So it's the capital accumulation side. Then you see the straight orange line that basically captures the effect of population growth, technological change, and most of all, capital depreciation. And you see that the point where capital accumulation, the red line, is basically cutting the orange line of depreciation, that is the equilibrium of the model. If the red line is above the orange line, there's more capital being accumulated as capital depreciated, so the overall capital per effective worker is increasing. That's the arrow to the right side. On the other hand, if capital depreciation is higher than capital accumulation, left side, you see the capital stock being decreased until it reaches the equilibrium. And in contrast to the Harrod-Domar model, this equilibrium is stable, meaning if you're pushed a little bit to the right, then the higher capital depreciation will lead for the whole model to adjust again towards the equilibrium. If you're pushed to the left, capital accumulation will be more than depreciation, so it will be pushed back to the equilibrium. So this nicely illustrates not only the functioning of the model, but also how it differs from this inherent instability of the Harrod-Domar model. And it's very important, again, to reiterate how important this factor has been for the Solow-Swan model success, because I would like to talk a little bit about the context. So Harrod-Domar, as I said in the beginning, Great Depression, rise of Keynesianism, planning affinity of the people given the successes of the Soviet Union, this is what determined their view on the economy. Solow-Swan, very different story. We are now in a situation where we have this post-war prosperity, especially in the West. There has been a rise in living standards. So this idea of a model where capitalism is presented as being stable is more consistent with what people were perceiving around them. This idea of factor substitution, the fact that you can substitute capital for labor and vice versa, is something that many people were experiencing in their daily lives, where firms actually substituted workers for more capital. So you saw that actually happening, and that was an important justification for preferring this model. On a political side, this model was often used as a defense of market capitalism during the Cold War. An argument that free markets are working, they are self-correcting. You don't need the planning intervention that is common for the Soviet Union and their idea of socialism. And then also what I mentioned before, this contact to microeconomics, the fact that the production function and everything else can also be derived from microeconomic theory. This has been something super important, especially for the rise of the dominance of neoclassical economics within the field of economics. So what Solow was doing with this model was really to actually opening up the possibility for an economics that overcomes the strict distinction into microeconomics and macroeconomics, but having micro-founded macroeconomics. Something that many, especially Keynesians, were criticizing a lot, but it is definitely one important factor explaining the success of the model. So in all, you could say, I think it's fair to say that Solow-Swan had some clear scientific advantages over the Harrod-Domar model, but it's also important to note that it fitted better the then dominant ideology. So this was maybe not the reason why it has become the most important model, but it definitely contributed to that fact. Finally, as of today, well, it's beyond doubt that Solow-Swan has been much more influential. If you look into a textbook for economic growth, Solow-Swan is where it all starts with. Is it better? I don't know. I mean, there's a lot of debate, especially after the financial crisis in 2007 and the many crises we witness afterwards, where people make arguments, okay, hey, this is actually exactly this kind of instability predicted by the Gräbner-Radkowitsch model. So we are operating in situations where these three growth rates are not the same, and the fluctuations and everything, the crisis we see, it's happening for endogenous reasons. Other with a different normative starting point will argue differently, and there's a lot of debate. So I think there are these clear scientific advantages for Solow-Swan, but the one that better fits reality, well, there's a debate about that. Although, as we will see later, while these models are often used as a starting point for economic theorizing of growth, there is also no doubt about them neglecting a lot of important factors. So if you ask an economist, hey, what's your favorite growth model? Many people will say, okay, hey, Solow-Swan is actually maybe the favorite one because it's so simple and it started this whole debate. But if you want to have something that really explains reality, you need to look at something more complex. I think that is definitely clear. And this is one reason for why many people would make this argument, because the Solow-Swan model makes a very strong prediction regarding global inequality. It predicts absolute convergence across country. What is meant by that? Let's look again at the mechanisms that are depicted in the Solow-Swan model. This is a figure showing basically the diminishing returns to capital. Remember that I said that this was one of the key innovations of the model. You see in the x-axis capital per effective worker, and on the y-axis the marginal product of capital. You see that if there is very few capital, you see that the marginal product of capital is very high. If you go to the right of the economy of this diagram, you see that the marginal product of capital decreases. I added here two situations: poor country with little capital and rich country with a lot capital per effective worker. You see that the marginal product of capital in the poor country is much higher than in the rich country, because the rich country already has a lot of capital, so the effect of having even more capital is much smaller as compared to the situation in the poor country. This is the formula. Marginal product of capital is basically the derivation of total output to the capital stock per worker. And this is the formula we get. If you want to print the figure yourself, that's the formula you need to use. And as you see from the figure, the marginal product of capital in poor countries where there's less capital is higher than in rich countries. Now from that, it implies that the growth rate of capital, or the growth rate of capital per worker, depends also on the current state of the capital per effective worker. We know that for rich countries, this growth rate in the model is higher than for poor countries, because the growth of capital is the change in the capital stock per worker divided by the total capital stock. And if you put into it the equations from before, you basically see that the growth of the capital stock in poor countries is higher than in rich countries, also because of the marginal product of capital being higher in poor countries as compared to rich countries. So basically, the model suggests that whenever you look at two countries, the one with fewer capital will see higher growth rates in capital accumulation and thereby in total production. This implies, obviously, that poorer countries grow faster than rich ones, so there is a converge. So they are converging to the living standards of the rich. This is an empirical statement that has sparked huge literature about that. And this idea of absolute convergence hypothesis, in the long run, all countries converge to the same per capita income, because growth rates in poorer countries are necessarily higher than in rich countries. That's a Solow-Swan prediction. Not really sure whether this is actually happening. People have been quite skeptical about that. It sparked a different hypothesis as well, the idea of conditional convergence. where people say, okay, maybe not all countries converge to the same level of income, but all countries with the same fundamentals, so important properties of their economy, they converge to the same per capita income, but not all countries. And I think the big contribution of the Solow-Swan model is that it has sparked this huge empirical debate about convergence. Yeah. If you want to test it yourself, you basically need to regress initial GDP on average growth rate. So this is basically how you would do it. On the left, you need data for 2 time steps. This is YIT and YIT plus T. You can then compute the average annual growth rates of GDP per capita over the whole period. That's what you see on the left-hand side of the equation. And then on the right-hand side, you basically see the initial level of GDP. And what you're mainly estimating is the parameter beta. The parameter beta indicates of whether those countries with a higher level of initial GDP suffer from smaller growth rates as those countries who start with a lower level of GDP per capita. So the prediction of the Solow-Swan model is basically that if you do this regression, you would see a beta parameter that is significantly smaller than 0. And if you looked at it in a visual way, this is how you would see it. We have here on the y-axis the average annual growth rates, here in this example between 1990 and 2022. And on the x-axis, the initial GDP per capita in the first year, 1990. And you see that the higher the GDP, the smaller the growth rates. So you see a significant and negative beta value. This is how the whole thing would look like if Solow's prediction held true. But my suggestion is actually that you find out that yourself. This here is not true data. It's data that I have simulated according to the Solow model. On the course webpage, you find an exercise where you're basically asked to get data yourself, to run this regression for different time periods, for different sets of countries, and to see to what extent this absolute convergence hypothesis holds or not. And before we continue with the rest, I strongly recommend you to do it, to try it out. You also get the solution on the course website, but I think it's a nice exercise to try it for yourself before that. If not, you can also read the conclusion. But I guess it's good to have a look at that before you actually continue with the rest of the lecture.